Introduce the Schrödinger equation to a complex, real-world atomic structure, and you immediately hit a mathematical wall. For the vast majority of systems in nature, exact analytical solutions do not exist. The interactions are simply too mathematically turbulent. Once physicists step away from idealized models, like the simple harmonic oscillator or the hydrogen atom, they are forced to approximate. The primary mathematical tool for handling these complex realities is perturbation theory. The method relies on a baseline. We start with an unperturbed Hamiltonian, a simplified quantum system that we already know how to solve perfectly. To this baseline, we add the perturbation. We scale this new term with a mathematical parameter, lambda, that we conceptually dial from 0 to 1. We then assume the true energies of the system can be expressed as a power series expansion of this tuning parameter. But relying on an infinite series approximation carries a distinct mathematical risk. If the terms do not converge, the entire calculation yields garbage. To rely on this theory, we have to define its limits. We need to know exactly when this approximation fails and under what conditions the series diverges. To find that breaking point, we test perturbation theory against a system we can solve exactly. We use the simplest non-trivial model in quantum mechanics, the two-level system. We define the unperturbed system as a 2x2 matrix. The known energy states, EA and EB, sit on the diagonal. The off-diagonals are 0. Next, we write the perturbation matrix, placing coupling elements, VAB, on the off-diagonals, scaled by our tuning parameter lambda. Adding them together gives us the complete perturbed Hamiltonian matrix for our test system. By calculating the exact solution for this matrix and comparing it against the perturbative power series, we map the exact boundary where the approximation collapses. First, we establish the absolute ground truth. We derive the exact eigenvalues of our test matrix using its characteristic equation. This handwritten equation shows the exact analytical solution for the energy levels. Under the square root, we have the squared energy gap plus the squared coupling strength. In a generalized problem, you also have diagonal shifts, labeled here as VAA and VBB. For our test, we set those diagonal elements to 0, isolating the pure off-diagonal coupling. This square root expression represents the exact physical truth of our system's energy levels. If perturbation theory works, it must match this equation. We now map this exact square root to the series of integrals found in standard textbooks. We bridge the gap by expanding the exact square root using a Taylor series with respect to lambda. When we perform the expansion, the first term maps perfectly back to the unperturbed energy state. Notice that there is no first-order correction for the off-diagonal coupling in this specific expansion. The next non-zero term is scaled by lambda squared. The math aligns perfectly. The standard second-order perturbation formula taught in quantum mechanics is identical to the Taylor expansion of our exact matrix solution, but expanding a square root into an infinite polynomial series carries a strict mathematical constraint. A core rule of calculus states that this type of infinite series only converges if the absolute value of the expansion variable is strictly less than 1. When we substitute our quantum matrix variables back into that convergence rule, we get this inequality. Simplifying it isolates the coupling strength relative to the energy gap. This establishes the rigorous physical boundary. Perturbation theory is only mathematically valid if the off-diagonal coupling matrix element is smaller than the gap between the unperturbed energy levels. This forces us to stop and ask a critical question. What happens if EA exactly equals EB, creating a degenerate state? At degenerescency, the energy gap drops to 0. The denominator in our expansion becomes 0, and the series violently diverges. This dictates why physicists must use degenerate perturbation theory. Diagonalizing the subspace before proceeding is the only way to avoid mathematical collapse. We can observe the physical behavior of these interactions by analyzing the signs of the second-order energy shifts. The higher energy level, EA, takes on a positive shift, pushing it upward. The lower level, EB, takes on a negative shift, pushing it downward. This handwritten graph maps the system's energy levels on the y-axis against the perturbation strength on the x-axis. As the perturbation strength dials up, the energy levels actively repel each other instead of intersecting. In a quantum two-level system, the shared denominator in the perturbation expansion guarantees that interacting states will repel and actively avoid crossing. Why is an exact crossing of these energy levels mathematically prohibited when tuning just the single perturbation parameter, lambda? To prove why, we map the generic two-level Hamiltonian onto the foundation of quantum spin, the Pauli matrices. In this equation, the d-vector components correspond to the Pauli matrices for the x, y, and z axes. This equation defines the exact eigenvalues for this Pauli-mapped system as the square root of the sum of the squared vector components. The strict condition required for a true crossing is degeneracy. The positive and negative roots must equal exactly 0. The sum of squared real numbers can only equal 0 if every single component is exactly 0. You cannot tune 3 independent structural variables to 0 simultaneously by turning just one mathematical knob. True level crossings are mathematically prohibited in two-level systems. Unless constrained by strict fundamental symmetries, the mathematical structure of quantum mechanics demands that energy levels will always repel.